Good morning. I am Krishna Kumar from Krishna's classroom. Let us continue from where we left in the discussion on diagonalizable operators. In fact, last time what we discussed was diagonalizability, and in fact, in between we talked about projection operators, which we would be requiring very soon in our analysis. So let us recall where we stopped. We characterized diagonalizability, or just a definition mainly. T is diagonalizable if and only if there exists a basis for V consisting of only eigenvectors of T. Which means if T is given, we can find, because the dimension of the space is assumed to be n, what we want is a set of linearly independent vectors, n vectors in fact, which form a basis for the vector space. And at the same time, these vectors should be what are called the eigenvectors of T. Then T is diagonalizable. It is a necessary and sufficient condition. In fact, we shall prove the following theorem. So, theorem. This is certain equivalent statement related to this. So let T belong to A. B is as given above. Let lambda 1, lambda 2, lambda k be the k distinct eigenvalues of that means lambda I is different from lambda j whenever I is different from j. Let Wi defined as a null space of G minus I. Then the following are equivalent. The following statements are: the first statement is diagonalizable. The second statement is this is equivalent to the characteristic polynomial of these f of x equal to gk and dimension of wi equal to df. third statement is dimension of dimension of W1 plus dimension of W2 etc. dimension of Wk equal to dimension of V. Okay, just give a brief proof of this. Now, what we have found last time is that in general, the algebraic multiplicity of an eigenvalue, namely, see here lambda 1 is an eigenvalue of algebraic multiplicity d1, and the dimension of the corresponding null space may be some number which in fact lies between 1 less than or equal to, say whatever that number is. I think I have used mi, say mi less than or equal to dn. Okay, right. So what we have is the following. What we have proved is this. If fx is in fact okay, what we have proved is the following. That is dimension of W equal to K and dimension of Wi equal to some mi, where 1 less than or equal to mi less than or equal to di, where di is the number of or what you call the algebraic multiplicity of di is the algebraic multiplicity of lambda. Now this number mi is called the geometric multiplicity of lambda I. That means the dimension of the null space of lambda I minus t is mi, and it is called the geometric multiplicity of lambda I. This mi is called mi, which is equal to dimension of the null space of is called the geometric multiplicity of lambda I. So what it means is that the geometric multiplicity of lambda I may not be equal to algebraic multiplicity of lambda I. The geometric algebraic multiplicity. Now, an example is where the characteristic polynomial is I believe this the example we have looked at is whole square. This is corresponding to this is the case corresponding to the following. I'll just this is V is taken as P to R and V is taken as the ordered basis is taken as 1x squared. And then T is defined, T belonging to LV is defined by so let me put here the mark. It's defined by T1 equal to 3 plus 2x plus 2x squared Tx equal to 1 plus 2x plus 2x squared and Tx squared equal to minus 1 minus x, and then extend that to the whole space. This is the example, and there of course the characteristic polynomial is lambda minus 1 into lambda minus 2 whole square. Now what happens in this case is that we have W1 and W2. Okay. We have W1 and W2. And here W1 which is equal to the null space of I minus T, which is essentially equal to the span of 1 plus 2x squared, and W2 null space of 2i minus t which is equal to 1 plus x plus 2 square. Here you see that dimension of is also equal to 1. Okay. So the eigenvectors, linearly independent eigenvectors that you can use to build the vector space is not sufficient because only 2 such vectors are available, whereas the dimension of the vector space is 3. Okay. So in fact, because of this, you see that dimension of W which is equal to 2 and which is less than 3. Therefore, in this case, P is not diagonalizable. So this is an example where the null space of T minus lambda I or null space of lambda I minus T, whichever way you want to call it, is not equal to the algebraic multiplicity, whereas the algebraic multiplicity of 2 is essentially equal to 2. The eigenvalue 2 is essentially 2, but this is the geometric multiplicity is not equal to algebraic multiplicity. That's the problem. Now I think this example gives some insight into the possibilities that you may have situations where we may not have sufficiently many linearly independent eigenvectors to span the whole space. That's a problem. So now we go back to our theorem, go to the proof of the theorem. Assume, see, this is the cyclically we do it. Usually we do it like this. Fine. This is one of the methods. Then everything, each statement implies the other. So this is the strategy that we are going to adopt. Okay. So we assume what? That means T is diagonalizable. What does it mean? It means that you can find a ordered basis, and with respect to this basis, the matrix representation is a diagonal representation. Okay. So what we have is this. See, there exists for me with diagonal elements the eigenvalues of T each repeating ni times, or what you call that I have used this, di times, where di equal to algebraic multiplicity of or simply write e repeating di times. Okay. Then what happens? If so, see that is that. See, this one is a d1 cross d1 matrix, and this is a dk cross dk. What is the consequence? The consequence is that determinant of this is equal to which is essentially the characteristic polynomial associated with this. Of course, what I have written here, this is with a possible change of sign. Okay. Right? I will put it this way. Determinant of minus this is equal to this matrix minus this matrix. So this is equal to the now this is the characteristic one. Okay, and this is equal to, we have seen this, that determinant of because we have seen that irrespective of the matrix representation that you have, because you can choose any ordered basis and get a matrix. For all matrix representations, the eigenvalues are the same, with the same multiplicity. Okay. Therefore, you see that the determinant of this, that is the characteristic polynomial for every one of those matrices, are the same. Okay, and that turns out to be this, because we are assuming it is diagonalizable. Therefore, there is a diagonal form, and for the diagonal form, we can exactly calculate this, and that is given by this. Therefore, we have this. The characteristic polynomial of t is this one. And we also have, in this case, okay, in this case, we observe that the null space of TB, is equal to, has dimension, or null space of TB minus lambda II, its dimension is equal to null space of T minus lambda I. So we get the required result. Null space of and further dimension of Wi is equal to dimension of null space of E minus lambda I by definition, and this is equal to dimension of the null space of minus which is equal to dA. Okay, so that's exactly what we have. Okay. Now what one has now is this. Therefore, we immediately have the following. That is dimension of Wi equal to Di, which implies dimension of W this is equal to D1 plus dk, which in fact is equal to n, which is equal to dimension of v. What does this do? Okay, that's exactly true. So hence so we have proved 1 implies 2, 2 implies 3, and 3 implies 1. Now we what does this mean? What are the elements of Wi? The elements of Wi are the eigen functions of T or eigenvectors of T belonging to the eigenvalue from that. Now we know that W1, W2, etc., Wk are independent. What I will say is linearly independent, which means what we have is this. Whenever I is different from A. So what is the consequence? The consequence is that, you see, we have Wk is equal to V, because these are independent subspaces and each has dimension d1, d2, etc., dk, and we already know that because of this d1 plus d2 plus etc., dk is equal to n. Okay, it's equal to dimension of V. That's what we have assumed. Okay, therefore basis consisting of eigenvectors of T for B. What does this mean? This is simply diagonalizable. That is, so we have proved 1 implies 2, 2 implies 3, 3 implies 1. Okay, therefore we have these statements, these three statements equivalent. It's a very useful concept. Now we shall also make one observation that whenever T is diagonalizable, then Ft equal to 0. So we shall prove this. Here. Suppose polynomials f of so prove the following. We are assuming T is diagonalizable. This means there exists eigenfunctions b1, b2, etc. bn, which are eigenvectors of T which span the whole space. Okay. Now let us make certain remarks. Let distinct eigenvalues of T and WIB equal to dimension of the null space of T minus I. Okay. Let dimension of WI be equal to 0. Then the diagonalizability of T assures that dimension of Bn, that is the algebraic multiplicity is equal to the geometric multiplicity. Okay. Therefore, and of course d1 plus dk equal to k. Therefore, let us write down that. Okay. So let UIDI WI. Then what do you have? We have P of Uij equal to lambda I Uij for di, and this is also true for, now we form a basis. And what we have is the B, which is defined as B1, Bk, which is equal to, write it down explicitly. You can write down U11 1B1 U21 form an ordered basis for B. What is the consequence? Now let us compute this. Let V belong to Q. Then V has a unique so what you have is that UB can be written as sigma C Cij J running from 1 to Di and I running from 1 to K with the Cij. These are uniquely now let us compute this. What is Ft of B? Ft of B is in fact the product P minus Bk operated upon. Now we observe that these factors do commute. And further, P minus lambda I of Uij. This is equal to 0. This is true for J running from I running from which implies Ft equal to so what we have proved is that if T is diagonalizable, Then for the characteristic polynomial f of t is equal to 0. Okay, right? Where ft is defined in this way. So you can, if you want, you can write. Okay. So for every v of t v equal to 0, which implies ft equal to 0. In fact, a much more general result is valid, which we are going to prove soon. Because this assumption that t is diagonalizable is redundant. Okay. Of course, the particular proof that we have given here makes use of the diagonalizability of t. However, one can prove the same theorem without any assumption that t is diagonalizable. In fact, for all f belonging, for all t belonging to LV, one can prove that ft equal to 0 for every t, for the characteristic polynomial f of t. Okay, this theorem is valid without this assumption. Okay, so I'll make a remark. This is called the famous Cayley-Hamilton theorem, which we shall need later, and we will certainly prove this. But for the time being, we will proceed to it, but we cannot use the same technique to prove that. Okay. Remark? Without the assumption of diagonalizability t, this result is valid. That is irrespective of whether t is diagonalizable or not. It is a 0 of the characteristic polynomial. That is irrespective of the property t is diagonalizable or not. T is diagonalizable. Ft equal to 0. Ft equal to 0 for the characteristic polynomial. F of t. Now this is called the Cayley-Hamilton theorem. This is see, the point is this. It's very easy to prove using this diagonalizability. But the proof there is going to be different. Okay? So the same, the proof we have given here does not work in that case. Whereas we are saying that it can be proved without that. So you need a different strategy to prove the theory. Okay. One corollary that you can immediately write is this is also quite relevant. Suppose T is diagonalizable. The characteristic point will be f of x be given by f of x equal to where d where lambda 1 being distinct eigenvalues of t, and they are of multiplicity d1, d2, etc. d3. This is algebraic basis. And you know that the algebraic multiplicity equal to the geometric multiplicity, since we have assumed that t is diagonalizable. Okay. Let gx be defined by this is quite easy to prove. You prove the same way. Exactly the same arguments are repeated. Use diagonalizability, and this is true. One thing that I want to assert here is that if T is not diagonalizable, okay, then F may not break down to a product of linear factors, and G also may not have this property. Although Ft will have this property, but Gt may not be. This is a distinct. Okay. Now this is a very important lesson. So we shall recall this, and the proof is now one remark that I want to make is that if T is not diagonalizable, the above corollary We shall see later, have a discussion on this later. Although the above theorem is valid. Now I will come back to return to this particular corollary later, and we will have a discussion on this. Okay. So I think this is a place where we stop now, and we will now do what is called the resolution of the vector space as a sum of W1 plus W2 plus etc. Wk, and then we also subordinate to this resolution, we will give a resolution of the identity operator in terms of projections onto W1, W2, etc. Wk. Okay? Right? And consequently, what form T takes up in terms of these projections. Now, these are the structural results that we will be working on. Okay? Thank you very much.